Have you ever wondered why the sea level rises and falls regularly? Today, we dive into the fascinating world of lunar influence and its role in creating Earth's tides. This cosmic interaction, a dance between the moon and Earth, drives the ebb and flow of our oceans, shaping the dynamics of our coasts and the rhythm of oceanic life. So if you've ever stood by the shoreline, watching the tide come in or recede, remember, the answer lies in the gravitational pull of our closest celestial neighbor, the moon. Gravity, as described by Sir Isaac Newton, is the invisible force that pulls two objects toward each other. It's this gravitational interaction that plays a pivotal role in the dance between the moon and Earth, particularly noticeable in the rhythmic rise and fall of our sea levels. Now, let's dive into the specifics. Newton's law of universal gravitation states that every mass attracts every other mass. The strength of this attraction is directly proportional to the product of their masses and inversely proportional to the square of the distance between their centers. In simple terms, the bigger the objects and the closer they are, the stronger the gravitational pull. Now, the moon is much smaller than Earth, but it's also much closer to us than any other celestial body. This proximity allows the moon to exert a gravitational pull that significantly impacts our planet's oceans. So the moon, despite its smaller size, has a significant gravitational influence on Earth, especially on our oceans. The moon's gravitational pull doesn't affect Earth's waters uniformly. This simple fact leads us to a fascinating spectacle of nature, the formation of primary and secondary tides. Let's start with the primary tides. As the moon pulls Earth's waters towards itself, it creates a tidal bulge, a sort of elongation of the water body, on the side of Earth directly facing the moon. Now, you might think that this is where the story ends, but it's not. There's another bulge on the exact opposite side of Earth, away from the moon. This might seem counterintuitive, but it's actually due to the centrifugal force created by Earth's rotation. This force pushes the water outwards, creating a second bulge. These two bulges on opposite sides of the Earth are what we call the primary tides. But that's not all. There are also secondary tides. These occur when the gravitational forces of the moon create additional, smaller bulges along the Earth-Moon axis. These secondary tides add another layer of complexity to the intricate dance of our oceans. So as Earth spins on its axis, different parts of the planet move through these bulges, causing the oceans to rise and fall. This rise and fall is what we experience as high tide and low tide. These tidal bulges are responsible for the phenomenon we know as high tide and low tide. This is the power of the moon's gravitational pull, shaping the rhythm of Earth's waters. Opening, the moon's orbit and Earth's rotation result in a rhythmic dance of tides. Our planet spinning on its axis, coupled with the moon's orbit around us, creates a fascinating pattern in the rise and fall of oceanic waters. This celestial ballet gives us 2 high tides and 2 low tides approximately every 24 hours and 50 minutes, a period we refer to as a tidal day. Now, the moon doesn't simply orbit the Earth in a solitary dance. It shares the cosmic stage with the sun. The alignment of the Earth, moon, and sun, our 3 main dancers, influences the tidal pattern. This alignment changes as the moon orbits the Earth, leading to different lunar phases. When the moon is full or new, it lines up with the Earth and sun. This alignment causes the gravitational forces of the sun and moon to combine, producing higher high tides and lower low tides. We call these spring tides, not because they occur in the spring season, but because the tide springs forth. On the other hand, during the first and third quarters of the lunar phase, the Earth, moon, and sun form a right angle. This arrangement results in neap tides, where high tides are lower and low tides are higher than average. Closing. So the alignment of the Earth, moon, and sun during different lunar phases results in varying tidal conditions. While the moon is the primary driver of tides, the sun isn't entirely out of the picture. Indeed, the sun, with its enormous mass and gravitational pull, also exerts an influence on Earth's tides. Remember, gravitational force is proportional to mass and inversely proportional to distance. While the sun is about 400 times further from Earth than the moon, its mass is about 330,000 times greater. This combination of distance and mass means that the sun's gravitational pull on Earth is about half as strong as the moon's. Consequently, the sun's influence on our tides is not as pronounced, but it certainly contributes to tidal variations. When the sun and moon line up with the Earth during a new or full moon, their combined gravity amplifies the tidal effect, creating what we call spring tides. Conversely, when the sun and moon are at right angles during the first and third quarter moons, we get neap tides with less pronounced highs and lows. Thus, the sun and moon together choreograph the intricate dance of our tides. The Moon-Earth gravitational interaction has far-reaching consequences. One of these is a process known as tidal friction, a subtle but game-changing aspect of our Earth-Moon dynamics. But what exactly is tidal friction? Well, it's a phenomenon that occurs as the gravitational tug of the moon creates tidal bulges in Earth's oceans. As Earth spins, these bulges attempt to align themselves with the moon, creating a kind of drag on our planet's rotation. This drag is what we call tidal friction. The effects of tidal friction are not immediate, but over millions of years, they accumulate. The continual friction slows down Earth's rotation, ever so slightly lengthening our days. If you could time travel back to the time of the dinosaurs, for example, you'd find that a day was only about 23 hours long. But that's not all. As Earth's rotation slows, it transfers angular momentum to the moon, causing it to gradually recede from us. In fact, the moon is pulling away at a rate of approximately 1.5 inches per year. This might seem insignificant, but over billions of years it adds up. So the dance between Earth and moon is slowly but surely changing over time. The moon's gravitational pull affects our tides, but it also affects the very dynamics of our planet and its celestial partner. This is the power of tidal friction in our Earth-Moon relationship. The moon's influence doesn't stop at the water's edge. The gravitational pull from our lunar neighbor not only affects the oceanic tides, but also has a profound influence on our coastal environments. Tides are not uniform across the globe. Depending on the geographical factors, such as the configuration of bays and the shape of coastlines, tidal ranges can vary significantly. For instance, in places with narrow funnel-shaped bays, the rise and fall of water can be dramatically amplified, leading to the highest tides in the world. Extreme tidal ranges can give rise to fascinating phenomena like tidal bores, where the incoming tide forms a wave that travels up a river or narrow bay against the direction of the river's current. Tidal bores are not just a spectacle for sightseers, but they also play a crucial role in shaping the coastal and river ecology. Furthermore, the continual ebb and flow of tides cause significant erosion and deposition of sediment along the coastlines, constantly changing and shaping our shores. This dynamic process creates a diverse range of habitats, supporting a rich variety of coastal and marine life. The tides also play a vital role in the transport and mixing of nutrients, influencing the productivity of coastal ecosystems. Therefore, the moon's gravitational pull doesn't just create a rhythmic dance of the seas, it also plays a significant role in shaping our coastal landscapes and ecosystems. As we can see, the moon's gravitational pull plays a significant role in shaping our coastal landscapes. Understanding the moon's influence on tides isn't just for astronomers or scientists. It has real-world applications that touch many aspects of our lives. Take renewable energy, for instance. The constant ebb and flow of tides, driven by the moon, can be harnessed to generate electricity. This form of power, known as tidal energy, is renewable and environmentally friendly. Then there's maritime navigation. Knowledge of tides is invaluable for sailors and ship captains navigating the vast oceans, as tides can significantly affect the depth of waters and the accessibility of ports. Even in aquaculture, the rising and falling tides, influenced by the lunar cycle, play a vital role in the cultivation of marine and aquatic organisms. And let's not forget coastal infrastructure planning, where understanding tides can help in designing structures that can withstand tidal forces and prevent coastal erosion. So the moon's influence on our tides is not only fascinating, but also immensely practical. We've traveled from the moon to Earth's oceans, exploring the invisible ties that bind them. We've unveiled the intricate dance of gravitational forces, the tidal rhythms set by the moon's orbit, and the sun's subtle influence. We've peeked into the profound impacts on our coastal environments and the practical applications of tidal knowledge. This understanding underscores the crucial role of our celestial companion in Earth's tidal phenomena. Next time you see the tides rise and fall, remember the cosmic dance between Earth and its celestial companion, the Moon.